The most inconvenient question, cosmology, consists of just three words. What was before? 13.8 billion years. That's how long, according to modern estimates, our universe has existed. But what if all this time we've been wrong in thinking that the Big Bang was its true beginning? And if that is true, then one of science's most famous stories may need to have its first chapter rewritten. Today we'll explore why two of the most mysterious regions in the universe, its moment of birth and the center of a black hole, may turn out to be manifestations of the same unknown physics, and how this idea could completely reshape our understanding of the Big Bang. And we'll try to figure out what, in the end, was before. Let's begin. The hot Big Bang itself is not seriously disputed. The cosmic microwave background radiation is an almost perfect black body with a temperature of 2.72548 Kelvin, a relic from the time when the universe was about 380,000 years old and had cooled enough for electrons and protons to form neutral atoms, allowing light to travel freely. These tiny temperature fluctuations were not just random noise. They became the cosmic seeds from which everything large in the universe later grew: galaxies, clusters, and the vast cosmic web. So the main idea of the Big Bang remains unchanged. At some point, the universe really was much hotter, denser, and more uniform than it is today. But here comes the strangeness. Two classic puzzles. The first, the horizon problem. Ask why widely separated regions of the cosmic microwave background ended up at almost the same temperature, even though, under ordinary expansion, they should have not had enough time to exchange information before that light was emitted. That was another puzzle. Imagine a pencil standing upright on its tip. Even a tiny tilt quickly make it fall. By similar logic, the geometry of the universe should have become increasingly curved over time. But that did not happen. Even after 13.8 billion years, the geometry of the universe remains astonishingly flat. So flat that any small deviation in the early universe should already be clearly visible today. This is known as the flatness problem. Both mysteries hinted at the same idea. Perhaps something unusual happened in the very early history of the universe. In the early 1980s, the idea of inflation emerged. According to that, the universe underwent a brief period of extremely rapid expansion, so fast that a tiny region of space could have been stretched to sizes far larger than the observable universe. This cosmic stretching phase could smooth out irregularities, flatten the geometry of space, and explain why today such distant regions of the cosmos appear as if they were once part of a single whole. Let's try to answer the main question: what was before? So, if the singularity may not be a real physical object, but rather a sign, our equations stopped working, then what could actually be there? Today, there are several competing ideas. One of the most well-known suggests that the Big Bang was not the beginning of everything. According to this version, before the expansion, there was an earlier universe that was slowly contracting, but instead of collapsing into an infinitely dense point, it reached a limiting state and then bounced back. Some versions of loop quantum cosmology, quantum effects prevent matter from collapsing to infinity, turning a catastrophic collapse into a cosmic bounce. Another approach purposes an even more radical idea. Perhaps the question, what was before the Big Bang? It's not even correctly posed. According to the Hartle-Hawking idea, in the earliest stages, space and time may have behaved so unusually that the usual notion of before simply did not exist. This is a bit like asking, what's north of the North Pole? The question itself assumes a direction that loses meaning at that point. There's also cyclic models in which the universe passes through an endless sequence of cosmic eras. Expansion is followed by contraction, and then everything begins again. Other scientists propose a long phase of slow contraction before what we call the Big Bang. So far, none of these ideas has received decisive confirmation. Some face serious mathematical difficulty. Others look elegant on paper, but still lack observational support. But the most important point is different. Modern cosmology no longer treats the Big Bang singularity as a confirmed physical object. Today, it's increasingly seen as a warning sign, a place where our best theories break down, and where new physics is likely required. The same problem appears when we move from the birth of the universe to the death of a star. Massive star does not surrender to gravity without a fight. For millions and billions of years, it's held up by the energy of nuclear fusion. As long as reactions continue in its core, the resulting pressure pushes matter outward and resists collapse. But the fuel runs out. Then other mechanisms take over. Quantum effects can support the remnant as a white dwarf or a neutron star. However, even these have limits. If too much mass is compressed into too small a volume, one protective mechanism after another fails. Gravity begins to win every round. At some point, an event horizon forms, a boundary beyond which even light cannot escape. And here, the familiar problem appears again. According to classical general relativity, nothing can stop the collapse any longer. The collapse continues. Density increases. Space-time curvature becomes stronger and stronger. And eventually, the calculations again lead to the same warning sign that appeared in the story of the early universe, a singularity, a point where our equations began to produce infinities instead of physical answers. This is why Roger Penrose's work was so important. It showed that black holes are not just strange mathematical solutions hidden inside equations. They can be a natural outcome of gravitational collapse. And today, this is no longer speculation. The Event Horizon Telescope has observed horizon-scale structures around M87 and Sagittarius A. At the same time, LIGO and Virgo have detected numerous black hole mergers through gravitational waves. More recently, the GW250114 signal provided the clearest view yet of how a newly formed black hole sounds. This signal matched the expected ring down of a rotating Kerr black hole with remarkable precision. The area of the final event horizon was larger than the sum of the original ones, as predicted by Hawking's area law. Thus, the old question, do black holes really exist, has effectively been answered. They do. Now, a more complex question lies beyond the horizon. If everything outside behaves exactly as general relativity predicts, what happens when collapse reaches the point where general relativity itself stops working? It is inside black holes that modern physics meets its most serious problem. The issue is that two theories, each extremely successful on its own, meet here. General relativity describes gravity, stars, galaxies, and the evolution of the universe on the largest scales with great success. Quantum theory describes the world of elementary particles and microscopic processes with equal precision. Each has been tested countless times, but inside a black hole they begin to speak different languages. The problem became especially clear in the 1970s when Stephen Hawking showed something unexpected. Black holes should not be completely black. According to his calculations, they should emit faint thermal radiation and slowly lose mass. Given enough time, a black hole could fully evaporate. At first glance, this looks like a solution. But in reality, a new puzzle appears. Imagine throwing a book, a computer, or even an entire library into a black hole. All information about these objects becomes trapped behind the event horizon. If the black hole then completely disappears, leaving only nearly uniform thermal radiation, where does the information go? Is it lost forever? Quantum theory says this cannot happen. Information should not simply be erased from the universe. But the classical description of black holes seems to suggest exactly that. And this is only the first problem. A second one emerges deeper inside. If we trust general relativity and continue the calculations, collapse does not stop. Space-time curvature grows stronger and stronger until the equations again lead us to a singularity, a point where they fail. It's important to note that Hawking radiation has not yet been directly observed in astrophysical black holes. For stellar mass objects, it is far too weak for current instruments to detect. But this does not make the problem less serious. The information paradox and the singularity problem remain among the clearest signs that a crucial piece is still missing from fundamental physics. A theory that could unify quantum physics and gravity into a single description of reality. One of the most well-known attempts to address this is loop quantum gravity. Its core idea sounds almost radical. What if space itself is not infinitely smooth? We usually imagine space as a perfectly continuous stage that can be divided into smaller and smaller pieces without limit. But loop quantum gravity proposes a different picture. According to this idea, there exists a fundamental scale below which space can no longer be divided. Area and volume become quanta of geometry, the smallest building blocks of space-time. If this is true, then many of the infinities that appear in singularities may not be real features of nature, but rather a consequence of incorrectly assuming that space remains smooth even where it does not. Physicist Carlo Rovelli, one of the main developers of this approach, has long considered loop quantum gravity a serious candidate for a quantum theory of gravity. However, one important caveat remains. Despite impressive mathematical results, the theory is still far from complete. Some of its key aspects remain under active investigation, and no final experimental confirmation exists yet. Therefore, today, loop quantum gravity is considered not a solution to the problem, but one of the most promising paths towards one. Their significance in this context is narrower. They show what kinds of changes quantum geometry might imply. In cosmology, such mathematical approaches can lead to a bounce instead of a Big Bang singularity. Inside black holes, effective models may replace the classical singularity with a region of extremely high curvature or a transition into a geometry resembling a white hole. This is still not proof that nature actually works this way. However, it is a sign that the same conceptual tool may soften both the cosmic beginning and the final fate inside black holes. What about white holes? This brings us to one of the most unusual ideas, the so-called Planck star. In the work of Carlo Rovelli and Francesca Vidotto, following scenario was proposed. When a massive star collapses, gravity may compress matter into an extreme state, the so-called Planck density. But instead of collapsing into an infinitely small point, as classical theory suggests, the collapse may stop at a finite, albeit incredibly tiny size. For an object with a mass of the sun, this core would still be microscopic, on the order of 10 to the 12th meters. That's roughly a trillionth of a millimeter. But more importantly, even at such scales, it is still not a point. And that is the key turning point. From the perspective of an internal observer, this ultra-compressed state can quickly transition into a bounce phase, as if the compressed matter is trying to expand back outward. But for an external observer, everything looks very different. Due to extreme gravitational time dilation, this process stretches almost infinitely. This bounce appears frozen and becomes practically unobservable. As a result, a strange picture emerges. Not a singularity as an infinitely small point, but an object that has already passed its maximum compression stage. Yet it appears almost frozen to the outside world. In essence, it may be a kind of reflection of the early universe hidden inside a black hole. This is sometimes described as a frozen Big Bang image. This is not a standard term in physics, but it captures the idea well. Collapse does not end in a point of infinity, but transitions into a state where quantum gravity completely reshapes the usual picture of space and time. However, this is where rigor matters more than drama. Updated discussions from 2024 about Planck stars and remnants are part of an active theoretical program, not an observed astrophysical process. Some works describe geometries of a black to white hole transition. Others discuss final states resembling remnants. Still others explore Planck mass quasi-stable objects, which could even contribute to dark matter. Thus, the most justified statement is not that black holes end as Planck stars, but that the removal of singularities inside black holes is an active area of research in quantum gravity. And one of its serious directions predicts finite ultra-dense internal states, rather than literal points of infinite density. And here, finally, these two themes merge. Behind both lies the same question. Does space-time truly end in singularities, or are singularities merely a sign that classical approximations break down? In cosmology, the hot Big Bang is real, but the singular beginning may only be a placeholder for deeper physics. In black hole theory, the event horizon is real, but the classical singularity may be another such placeholder. If this parallel is correct, then the universe did not necessarily begin from an infinitely compressed point, and black holes do not necessarily end in one either. One answer would be that there existed a phase preceding the Big Bang, perhaps contracting, perhaps boundary-like, perhaps something that cannot be described by any classical model. Second answer would be that the final interior state of a black hole is not a point of failure for theory, but a regime where space-time itself becomes quantum. And if both answers are versions of the same idea, then the path to understanding what came before the Big Bang may run primarily through the physics of black holes. Meanwhile, the singularity remains the name of a limit, a point where old equations lose their validity, and a deeper theory must take their place. The answer will not come from speculation alone, will come from the next place where extreme gravity leaves a measurable trace, a cleaner ring down of such, a sharper map of ancient light, or a signal that does not fit existing rules. Until then, every black hole merger and every new glimpse of the early universe is not just another observation. It is another attempt to find where physics stops pretending that infinity is an answer.